Traditional computers use classical bits, that is, binary code, to store information. Classical bits have only two states, either 0 or 1. Quantum computers use qubits, which are quantum bits, instead of classical bits. Qubits can exist in superposition, being both 0 and 1 simultaneously, enabling exponential computational power. For example, 3 qubits can exist in a superposition of 8 states simultaneously, whereas a classical computer can only process one state at a time. Quantum computers solve complex problems, such as cracking encryption, much faster than classical computers. For example, Google's Willow chip, a quantum computer, solve a problem in under 5 minutes that would take a classical supercomputer 10 to the power of 25 years. Bitcoin uses two encryption methods, SHA-256 and ECDSA. SHA-256 is a cryptographic hash function used in Bitcoin primarily for two purposes: hashing transactions and mining. Each transaction in Bitcoin is hashed using SHA-256. This creates a unique digital fingerprint of the transaction data, ensuring that any tampering will be detected. Miners compete to solve a complex mathematical puzzle that involves finding a hash value below a certain target. This process requires significant computational power and ensures that adding new blocks to the blockchain is difficult and secure. Elliptic curve digital signature algorithm is used in Bitcoin for securing wallet addresses and signing transactions. Bitcoin addresses are derived from public keys, which are generated using ECDSA. The private key is kept secret by the user, while the public key is derived from the private key through elliptic curve cryptography. The public key is then hashed and encoded to create the Bitcoin address. When a user wants to send Bitcoin, they use their private key to sign the transaction. This signature is created using ECDSA and ensures that the transaction is authentic and has not been tampered with. The signature can be verified by anyone using the corresponding public key, but only the person with the private key can create a valid signature. A sufficiently powerful quantum computer could theoretically break ECDSA using Shor's algorithm, which would allow theft of Bitcoin from exposed public keys. To crack Bitcoin's encryption in 10 minutes, a quantum computer would require approximately 1.9 billion qubits. This is far beyond the capabilities of current quantum computers. For example, Google's Willow chip has 105 qubits, and IBM's Osprey processor has 433 qubits. Both are impressive advancements in quantum computing, but they are still far from the number of qubits needed to pose a threat to Bitcoin's encryption. Moreover, even if a quantum computer had the required number of qubits, it would also need to achieve a high level of error correction and stability, which is another significant challenge. Therefore, while quantum computing poses a theoretical threat to Bitcoin's encryption, it remains a distant concern with current technology. So, does Bitcoin have a defense strategy against quantum attacks? The answer is yes. The Bitcoin community has discussed quantum resistance since 2010 and can transition smoothly to quantum-resistant algorithms via a hard fork if threats emerge. Early Bitcoin, such as Satoshi's unmoved coins, uses legacy addresses with exposed public keys. If quantum computers advance, these coins would likely be stolen first, serving as a warning sign for the network to upgrade. Finally, let's talk about why there's no need to worry too much about quantum computing. Even with rapid progress, Bitcoin-breaking quantum computers are decades away, and the Bitcoin network can upgrade its encryption before quantum threats materialize. Meanwhile, banks, governments, and corporations using weaker encryption are more likely to be attacked first, as attacking Bitcoin is less profitable than hacking centralized systems. So keep your private key safe and don't worry too much about it. Thank you for watching this video.